see here is a stem and leaf plot. We call it a stem and leaf plot because this part is called the stem and those are the leaves. Stem and leaf plots are great provided you have a small sample and also a discrete sample. If you have, say, 1,000 observations or 10,000, you'll need lots of paper, just like a CVS receipt. So I don't know where they waste paper. So
I will let you know about all the deals you can get.
they're all overpriced anyway.
Oh, yeah.
So the purpose is to determine the shape, and you can see in this particular stem and leaf plot, you have a shape for both of the districts above there. If you look at that one, you have something like that. Yes, you have to tilt your head sideways without getting it spraying, and then you can determine the shape. So the shape is the most important aspect of data. So a stem and leaf plot also requires a key. The key helps us identify or helps us interpret the observation in the data. For instance, 2 /7 means 27. It doesn't necessarily have to be the first observation, but oh well. So what is the next observation?
32.
The next one?
41.
Next one?
43.
Next one?
43 again.
You get the picture, right? So 41, 43, 43, 44, 47, 47, and 48. So we will do an example where we're going to take all the numbers, put it up here. And I want to do something, and I'll show you in a bit. Asking for the minimum data, we can tell for minimum observation, that is 27. What is the maximum? 85. So interpreting this is not that difficult. Are you with me? Okay. So I want you guys to go ahead and write all the observations down by reading that stem and leaf plot. Well, we interpreted all observations from that stem and leaf plot, wrote them down. I want to create a frequency distribution. Let's just say, 5 classes. Where should we start? Where do we go ahead?
I think take 85 minus 27.
Keep going, have some faith in yourself.
Okay. And then you would divide that by 5, right?
So 85 is the maximum, 27 is the minimum, and what is that 5? The number of classes that we bought. So 85 minus 27 is 38. That would be 11.6. Yes. Now, the book says always round up. Once again, that is the book's approach. In practice, you can round it to the nearest integer. So we'll stick with what the book says. We have to round up always. And the data. Contrary to what we did, This is what the book does. Page 27 adds 12 to 27, which would give us 39. Add 12 to 39, we will get 51.
So 12 is the width, right?
Yes. Add 12 to 51, we get 63. Add 12 to 63, we will get 79. Good. It's just adding 12. And over here, we're just going to create that gap by going 1 less than 39. So 1 less than 39, 38. 1 less than 51, 50. 1 less than 63, 62. 1 less than 75, 74. And I've added 11 to get to 74. So I'll add 11 over here to get 8.
Where did you add 11?
So the book adds 12 as we go from class to class to the lower limit, right? Over here, since I started at 39, I have to go 1 less than 39, which is 38. So what is the difference between these two? That's 11.
Okay,
When you go here, 1 less than 51 is 50, and you have 11. Same thing. Yes,
so we're gonna do the 0.5 anymore?
we're getting there. Okay. Are we clear with this? Yes?
Yeah.
Okay, so adding 12. Adding 12. Adding 12. Adding 12. And each over here. 38 minus 27, 11. So the last class, we're adding 11. Good. It's about counting now. Let's count. Oh, what is the advantage of a standard leaf ball?
It's already in order.
It is in order. So lucky us. So 1, 2, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4. 1, 2, 3. Makes it easier for us. Previously, when we did this, we had to search through. Now we don't have to. The purpose of a frequency distribution is to create relative frequencies, ogives, frequency polygons, whatnot. But we can also create a frequency histogram. Think of the shape that I mentioned, or I showed you with that stem and leaf ball. We want to see if the histogram gives us a similar shape. Okay? Let's see. Are these called class limits or class boundaries? Boundaries, yes.
I thought there was a 44 in there. Yeah.
Where was the 44?
You just forgot to go.
In the data, there was a 44?
Yeah.
Oh, my bad. I'm sorry. Thank you. Write it and get rid of it. Okay. So what are these class limits or class boundaries?
Just boundaries.
These are boundaries.
Limits.
It's a limit.
They are limits, right? How do we create a boundary?
Minus.
Minus 0.5 plus 0.5. This once again goes back to, Schultz's pet peeve and mine too. Because what's the point of doing this? We could have done this from the get-go, right? So this is how, people explain frequency distribution. But that's okay, but it is not a pet peeve of mine. -27 0.5 is 26.5. 38.5. 13.5. 62.5. 74.5. 86.5. Add, subtract, subtract. So subtract 10.5 from 27, 26.5. Add 0.5 to 38, 38.5. Do the same thing till the very end. Those are the 5 classes that we can have. Firstly, what is the purpose of doing this? To make it continuous so that the bars are touching each other. Clearly, they don't know COVID regulations. Bad joke. Okay, not drawn clearly to scale, but oh. So the first bar, height is 2. The second one, 8. The third, 15. Okay. The next one, 4. Next one, 3. Last one, of course, 0, 0. Good. Isn't that similar to what we saw in that stem and leaf form? Only this time you don't get a spring. If you can't see that shape right away, what did we do previously to get that shape roughly? Connect the dots, very good. So we've, put a dot that's arbitrary, a dot there. Then dots at midpoints, we don't necessarily have to compute them in this problem, but if you have to find the midpoint, what is the midpoint of those two?
+38 divided by 2.
27 + 38 divided by 2, which would be 65 divided by 2, which is 32.5. Good. Okay, but here we don't have to, right? So draw a vertical line. And now connect the dots. So roughly, that looks like a bell curve, right? Not perfect, but it follows that shape. So this data is normally distributed. Does it have skew? So we went from stem and leaf plot, and here we are with a nice little curve that shows us the shape that the stem and leaf plot had before. Are we good? Yes.
I'm confused about the data. Is the way that you did it before was like add 12 and you just skip a line? Can you still do that, or it has to be that way?
You can still do that. Good
Okay, that
question.
makes, okay.
I'd
You
rather
can
do those.
still do that. I'm trying my hard to do it this way so that you don't make mistakes when it comes to my MATLAB. Because it only takes answers if done in this proper way, because it is strictly following the textbook. So that's why I mentioned, Jules always asks, okay, could I do it this way? Could I do it that way? Yes, there are hundreds of ways, but I'm going with this time so that you don't make mistakes.
Which way is it gonna be on the exam?
Very good question, Sarah. Close. Okay, close. Casey wants to know which way would it be on the exam? On an exam, you don't have to worry about creating the graph, period. I'm showing this so that you get an idea as to how that is connected to this. On an exam, I will give you the picture. All you have to do is interpret it properly. That makes sense. So don't worry about creating. I don't know why they put questions on creating the first place in my MATLAB, but don't worry about creation. Yes,
Did you say the exams are a hard copy or we can bring our laptops?
that. Any other questions? Yes.
You just said it, sorry, I didn't hear you, when you said we don't have to worry about making the graph, all we have to worry about is what?
Interpreting,
Interpret.
because I will provide you with the graph, you just have to get the information. Just like that problem, I gave you a stem and leaf plot, and I can ask, well, what is the maximum data? No, 85. So what is the smallest number or smallest lifespan that we see? 4, there's a 4. Someone probably spotted that one on the 4th day. 0, 1, 2, 3, 4, 5, 6. What's the highest? 14. 9, 10, 11, 12, 13, 14. So we've got 1 at 4. How many do we have at 4? Just 1. So we put a dot. How many 5s do we have? I see 1. A dot. How many 6s do we have? I see 3. So we put dot, dot, dot. How many 7s do we have? I see 3. How many 8s do we have? 1, 2, 3. I see 3. 9. 1, 2, 3. The dots have to be aligned. 10, 5. I'm counting 5. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. 11. 1, 2, 3. I don't see any 12s. There are 3 13s. There are 4 14s. Right, there are 3 in the second row, 1 in the first row. That's it. Do you see a shape of some kind? I mean, there is a shape, but it's just not a regular shape that one would encounter in stars. But this does give some information. If someone asked you, the average lifespan of a housefly, what would your answer be?
10 days.
Minutes? It's in days.
10 days.
Yes, it is.
It's in days. That poor fly. It's only for 10 days. So in days, so 10 days. Because would it be exactly 10 or in the ballpark of 10? Around 10, it's probably going to be here. There is a very high probability that a housefly would live past 13 days. Is that true or is it false? False. Why is it false?
Because the majority of, dead flies are Maine and, what's up with 11?
So majority of the flies, live up to, 11 days. What is the probability that a housefly would die within 3 days? None, 0%. Luckily, every single one of them live and then at least for 4 days. Do we understand this? But is this an effective plot? Not really. It worked here because the data is discrete. Do we agree? No decimal values. And we don't have a significantly large sample, relatively small. How many observations do we have? 30, reasonable. No decimal values. And the range is sort of compact. We have 4 to 14. Imagine if you have a different data set where you have some observations between 4 and 9, some between 20 and 24, and some between 100 and 150. And you want to put all of them in one single dot plot. Would that be reasonable? Messy, no good. Another case would be a larger sample. If you have a significantly large sample, you can say 1,000, then you'd have 1,000 dots on a piece of paper. Do you really want to look at 1,000 dots? No. So dot plots are okay. Stem and leaf plots are okay as long as the sample size is small, the data is discrete.